So, let's see at the back. Everyone's ready. All right. Our next speaker today is David Hanson. He has a PhD in interactive arts and engineering, combining robotics, cognitive science, and art. And I asked him, what does a guy with that background get into professionally? And he said, well, I went to work for Disney. And I went, as an Imagineer? And he went, I was an Imagineer. So that was one of my dreams as a child, to meet a real live Imagineer from Disney. And now I can die a happy man. So please join me in welcoming David Hanson. He's coming right down the aisle.
Former Imagineer, but thank you. Thank you very much. So it's an honor to be here at the Singularity Summit. It's such a special gathering for focusing on long-term issues. Many conferences focus on world-changing issues, but there's no issue that may change the world as much as the potential technological singularity. So my focus on approaching super intelligent machines is to emulate the human being as accurately as possible. This is an example of one of my robots. It is a portrait of Albert Einstein. I built the head, conversational personality, and then interconnected it with the body built by the Korean Advanced Institute of Science and Technology. This will show you a few examples of how human-like these robots can appear if we engineer them properly, design them well. It requires some advances in material science with this skin material, understanding of facial physiology, decreasing the power consumption of a full range of facial expressions so that it can mount on a complete body. Altogether, we can then study the entire human entity, human being, and then abstract this to realize what we know of intuitively as characters. We love characters in cinema, literature. They're a form of human-to-human interaction that is externalized into artificial media. In our case, we're not putting it into computer animation. We're trying to put it into algorithmic, AI-driven, physically embodied robotic characters.
Intelligence?
Or just artificial life forms. So for those of you who have not had a chance, you can step out into the lobby at some point and have a conversation with one of our robotic characters that we've brought, who's a portrait of Zeno of Alea. This little character is also called Zeno.
Oh, about an hour and a half.
Can you tell me a story?
So here you'll...
Sure, I can tell you a story. Here's a story called The Other Side. One day, a young Buddhist on his journey home came to the banks of a wide river.
So
Staring hopelessly at the great obstacle in front of him, he pondered for hours on just how to cross such a
Zeno
wide
can
barrier.
tell stories, have sort of natural flowing conversations. So my discussion today is going to be about the effect of intelligent character machines in the economy as a driving factor for achieving friendly artificial intelligence. I'm going to use some examples of the work that I've done just to show what may be possible in this direction, but I'm going to show some examples of other researchers and developers and corporations in the world who are making progress in this direction.
Your childhood friend? Would you want it on the laboratory?
Philosophically, an integration of multiple media, robotics, hardware, consumer product and manufacturing, artistry, and marketing are required for this kind of technology to take root in our world, to be meaningful in our lives. Now, the actual applications can be entertainment, so you can attach a story to these kinds of intelligent characters and have cross-media franchise plays so that it can be analogous to traditional character media and an extension of traditional character media. You can also utilize this technology as a new form of computing, the human-like computer.
Oh, hi, Amanda.
Hi, Zeno. How are you doing?
So I'm fine. I'm glad you're here.
Oh, good. I'm glad I'm here with you, too.
I love you.
I love you, too. You're a good boy.
You know we're shooting this video, right? And you can help me show off all the neat things I do. Okay.
Sure, I can do that.
Okay, great.
So, what are you going to show me?
Well, I can't show you how I understand what you're saying, right?
Like you just did. You understood me.
Exactly.
And you recognize my face, too, right?
Yeah, and I learn people's names and stuff.
And you know who I am, right?
Yeah, you're my mommy.
That's right, Bunny. So tell me, what else can you do?
Well, I remember what we talked about.
So what you see in this video is a nexus of numerous fields of AI, machine perception, machine learning, mechanical engineering, and material science research brought together into a character. Under controlled circumstances, such as a quiet environment with a well-trained acoustic model, the speech recognition works really well, and you can have relationships that are formed between people and the machines. These kinds of relationships, this emotional connection of people with machines, humanizes the machines and makes the machines more meaningful. So instead of mechanizing the human, we want to humanize the technology.
Hold on, Zeno.
Let me see if I can get this slide to advance from here. So we've developed about 20 of these robots, human-like robots, over the last 8 years in my particular group in collaboration with KAIST, University of California at San Diego, University of Pisa, University of Geneva. These are our partners that take the robots that we develop and apply them in cognitive science research, sometimes in collaboration with us, sometimes independent of us. One example of an excellent collaboration was an android portrait of Philip K. Dick, the science fiction writer who was responsible for Blade Runner and VALIS, which stands for Vast Active Living Intelligence System, the concept of a superintelligence in the future, kind of like a technological singularity, that arises naturally out of today's technology progress and cultural progress, not just technology, but the understanding of physics, biology, the humanistic traditions of the arts and literature, all can contribute towards making machines more capable of getting along well with people, becoming part of our culture instead of a deleterious force pulling our culture downward. So in the Philip K. Dick robot, we brought together conversational AI, some face tracking, and it ran it on a PC, and it was pretty good. Now, this was 2005, and since then you've seen some of the more advanced conversational capabilities, but we're still not there. They are not fully gratifying as characters. They don't seem like the protagonists that you would go to, say, a Pixar film to fall in love with. We fall in love with characters in our favorite novels. We fall in love with the idea of a hero going on the quest through life. We experience this ourselves. This is kind of how we frame ourselves. That's how our nervous system is built. And this is what we look for in our friendships and our relationships with people. How can we bring that to these kinds of machines? So here I've portrayed Zeno of Elea, the original Greek Zeno. And the concept is that as we approach super intelligent machines, can we also approach an essential humanity, computational models of humanity in the machines through this fusion of cognitive AI and art? If we can do that, then we can sort of tap into the human natural tendency for forming relationships. We are hardwired for social cognition, and it's incredibly complex. I mean, in fact, in neuroscience, you find that a substantial portion of the human brain, the visual cortex, is used for processing humans, human relationships, the language processing, this sort of distributed systems. They are grounded in this social intelligence system. We are individuals, and yet we are also socially intelligent creatures. And this brings a lot of value and comfort to our lives. And in order to understand human intelligence, then modeling human social cognition allows us to both understand human intelligence and also embody this kind of social intelligence in our machines for bridging machines and human, improving human-machine relations, i.e. Paving a path towards friendly AI. Now, there are some good examples in popular culture where fictional characters are not quite human, but they're human-inspired. We still fall in love with these characters. These movies that aren't exactly realistic, perfectly human-like, still can make us cry, can make us feel like these characters are thriving, suffering, overcoming obstacles, and we feel like the world grows. So this has a psychological utility. It's not frivolous per se, and we're hardwired to learn and grow culturally through these kinds of relationships. Fictional characters and human-to-human relationships, and this could extend to character machines. It could extend to robots and simulations if the intelligence is human-like enough for them to really act like protagonists, for them to act like people. So this power of character, it drives the economy of entertainment. Magazines sell because people are on the cover of magazines. We respond to faces. Faces sell, right? We like actors because they have a certain demeanor, a certain charm that comes through their physical presence. That's part of our intelligence, is knowing how to recognize that and respond to it and to read that. It's a very high bandwidth mode of communication. And in fact, in neuroscience, and cognitive psychology, there's very little of that nonverbal communication that is understood at this point. And the neural activity correlated with that nonverbal communication is also poorly understood. So there's great progress, but by modeling people, we can, through the robots and simulation, artistically, we get an avenue in, a way to make these kinds of machines work before we have a full, formal understanding, scientific understanding of face-to-face communications. Then we can do the science. We can find out why it works. It's a way for us to reverse engineer the mind of the artist and then turn it into first principles so that we can then engineer better machines. And that can inspire better art, so there can be this feedback loop between art, engineering, and neuroscience, and then the deployment of these units as product. And in the end, by developing these machines among us as our friends, to the point where they can understand us, then we can trust them. We desire them more. We are not wondering what they're up to, in their crazy black box of superintelligence. So it's important for us to define character for a moment. So character, first of all, means agency, ascribing a certain being to it, believing that there is a being there. For it to happen, for the illusion of life to happen, in this case, there has to be intelligence. We sense it if there's not intelligence. That's why character machines, as of today, are only just barely satisfying. We've got so much more to do in order to make AI come to life in the way that we expect for characters. So that illusion of life is very important. Now, in traditional media, like film animation and fiction, the characters are representative of the intelligence of the authors, of the animators, of the sculptors, of the directors, right? So that intelligence is in a way, a representation of the simulation within the mind of the authors. But in this case, for the characters to come to life, they have to be truly intelligent. So in addition to agency, an illusion of life, or maybe eventually true life in the machines, I like to think of moral character. When we think of protagonists, we think of characters that overcome adversity to have self-discovery. They find some kind of wisdom. They gain their accomplishments by honor. Those are the protagonists that are really satisfying. Otherwise, they're the kind of movies that people grumble about after they've seen the movie. So moral character is really important. So people innately respond to the human-like face. That's why character is important. That's why human-like computers and humanoid robots are a good paradigm for human-computer interaction. Newborns respond to faces. Our brain is hardwired for faces. 5-week-old infants use the same brain structures for perceiving faces and recognizing faces and facial expressions that adults do. It is hardwired. These are specialized regions and networks within the brain for social interaction. And for this reason, the characters really, really speak to us emotionally. And when we combine this innate response with our technology, then it opens up many opportunities for cultural adoption. People love these kinds of things. There are examples out there existing. Massive software was used to animate many of the characters in Lord of the Rings, iRobot, and Pixar films like Ratatouille. These are characters that are autonomous. They're rule-based. They're not learning systems, but they act alive, and they're really gratifying. But they're only the background characters. They're not the heroes. They're not the protagonists of the film. But in the background, you don't know that they weren't animated by people. So we're making progress. So massive software is one good example, but game AI in general is another example of product that is satisfying to people. There is a demand, a proven demand for character machines, autonomous character machines. More examples include the hot demand for virtual worlds, The Sims, toys. Furby, issued in 2005, the latest version had a speech recognition chip. It was $29, right? But it had speech recognition. It had motors that controlled a wide range of facial expressions, emotions. These kinds of toys and consumer products do sell, but they don't have enough life to hold our attention for a while. You don't feel like that, Furby was your friend, or even Aibo. Aibo sold 200,000-ish units, okay? Roughly $2,000 a pop. That was a real market. It was very satisfying, but people got bored of it because it didn't adapt. It wasn't creative. So there is a pain that can be satisfied by more intelligent characters. So now in research, you start to see a lot of machines that are much more capable than the ones that have been released as consumer products. You see a few of these being sort of tested, like in Disney theme parks, like the Lucky the Dinosaur. You have biped robots, wheeled robots. You have research robots with a wide range of facial expressions that are based on film animatronics. The robots are more capable. But most of these are very expensive. So there is a certain curve where the complexity becomes translated into very low-cost manufactured capabilities, and then these things get deployed. And when they do get deployed, they are popular. So, there exists some path from research to market. But the problem is that they really are not as intelligent as we would like. I mean, even the research robots don't have enough integrated cognition, and there is a separation generally in research between this artistic approach and the robotic approach. It's a very fragmented sort of research field. In addition, the human-like robots that were generated, when you're close to them, they just didn't feel like they were alive. They just feel kind of dead. The expressions weren't there, and part of that was the materials, which was part of what I tackled when I started my PhD work, diving into the material science to come up with a substance that I call frubber. That frubber is just one technique. It's a bio-inspired lipid bilayer porous silicone elastomer that allows very lifelike expressions, very low power. But the point is that if we can imitate the human identity, whether realistic or abstract, whether it's in the form of an animal or even a robot presence like a C-3PO or an R2-D2, there can be this kind of emotional connection between people and the machine. But we don't understand it. We don't understand the human mind. We don't understand how we perceive robots. We don't understand how we perceive each other. And so this kind of engineering is largely intuitive at this stage. I mean, it's a mix of pure engineering, art, cognitive science, and neuroscience, but doing it in a lab keeps it isolated from the kind of feedback that we really need. You know, if we've got, say, half a dozen people in a lab interacting with the robots that we've made, the information we get is very limited. If we have 24 people in a controlled experiment, then the kind of feedback we get is also extremely limited. By deploying it as product and then garnering data from users, we get a much clearer idea of how people actually respond to the robot, and you get an acceleration of that feedback between the user and the neuroscience and formal understanding. So here's the loop in essence. So we have some rough science of mind, understanding of mind. We have some experimental neuroscience practices, right? We've got some art practice for generating characters, and we've got artificial intelligence and robotics. Well, if you fuse these into a loop, and you formalize this loop, then you accelerate the development of artificial intelligence that can empathize with us, that we like. There's a pressure, a natural market pressure for machines with empathy. Machines that can like us, and maybe more than that, love us. And machines that inspire us to love them. It builds relationships with people and machines. And machines that are annoying, that are greedy, that are bad or evil will not satisfy consumers, right? You know, so those would not be the kinds of robots that you would want to buy. So there's this natural market pressure for good machines, machines that are part of the human family, if we bring that together. So it does involve an enormous number of disciplines. Biology, mechanics, it's like the Renaissance. Like, it requires this Renaissance philosophy where disciplinary boundaries are just blasted away, right? I mean, the disciplines are all there, but they're fused into a super discipline and redefined as new disciplines. So I'm going to skip because we're running out of time very quickly, right? Okay, cool. So, so this but it's an integrated biology approach to robotics development, and it involves latest technology in rapid prototyping, laser scanning. It involves classical sculpture. So this is going to give you an example of my process in developing some of these characters. This is a clay portrait of Einstein that I did by hand, and then I make a mold of this, and I cast the rubber in this mold with an anatomically accurate skin thickness. It's basically like a reverse facial, forensic facial reconstruction process. It's not just the rubber that's responsible for expressions in the robots that I'm developing, but also soft body tissue engineering. So how the force gets distributed through the skin makes the critical difference in whether the expressions look alive or whether they look, kind of grotesque. Still exploring that, so part of it is definitely in the rubber material engineering. So we've got 4 techniques in the material engineering. One is a macromolecular micelle, which is a 4 to 40 nanometer distribution of reverse micelles, little vesicles in the material that act as ripstops and also create microporosity, a nanoporosity in the material, and then also hierarchical porosity up to the macro scale. It makes the material extremely supple, very low energy, and also it makes it deform more like fluid-filled facial soft materials. That's what's responsible for our facial expressions. In addition, we have capacitive field sensing that we're experimenting with in the robots. Some of this work is done under National Science Foundation award. We were investigating piezo polymer actuators, a lot of piezo also electroactive polymer actuators and devices or artificial muscles. Some of the results are promising, but good old-fashioned motors are still just the mainstay. But it involves an expectation that these kinds of materials are going to advance in the future. But the faces are just a kind of interface, a 3D display technology, and maybe also a tactile technology. The physical embodiment makes a huge difference, but it's the software that we're here for. The cognition is the profound thing, and this cognition for human-computer interactions. Here is an example of the software that I have in the robots that we're developing. So you have some semantic representation of the world, you've got knowledge representation. It performs reasoning based on the vision that is coming in, face tracking, face perception, face recognition, face expression recognition. You also have the audio recognition with the speech recognition. Ideally, you have many other kinds of perceptions. You need to perceive where the sound is coming from, noises that are not speech. So it involves a massive fusion of knowledge, and this has to be adaptive in order to achieve something that's gratifying as a character. Okay, so you also need authoring tools. So in our software, we're collaborating with Kino Corsi, who's joined us here from Daxtron Labs. He and Doug Miles developed Cogbot. My team of really wonderful software engineers has worked with me to develop Character Engine. Matt Stevenson is here. Now, a substantial portion of this is made open source and is also built on other open source components. But then it interfaces with proprietary components like some of the machine perception that we're using. And connects to web services to answer questions beyond the domain of the internal knowledge base. Also looking at distributed computing infrastructure so that we can have some onboard computing as well as non-real-time processing, kind of an unconscious processing within the robots. Logically explicit awareness is the development of Kino Corsi of Daxtron Labs, and he's been exercising some of this with the Character Engine, so that the idea is that we're pushing towards models of consciousness. So some pure computational models, pure math models, but then also bio-inspired models of consciousness and self-awareness. Adaptive self-awareness and creativity is essential. The machines need to be able to make new structures come into existence, new solutions, new models of the world. It has to theorize. And and when humans are theorizing, it's not just pure science. It is also intuition. That creativity is essential for all discovery and creativity. All the invention is kind of outside the world of science. So we also have this thing called the Apollo Mind Initiative, which is a nonprofit parallel corporation dedicated to the quest to achieve greater than human level genius in machines by the end of this decade. So in collaboration through our Apollo Mind Initiative, we've combined in, we've interfaced with the Machine Perception Lab face expression recognition at UC San Diego, which uses wavelets to detect facial expressions and then classifies the facial expressions. And then we have facial expression mimicry. This shows the resulting robot that had also their audio localization, so it could detect where sound was coming from.
Let's see if it gets my facial expressions.
And here you have
so I'm smiling.
Detection of facial expression and mimicry of the facial expression.
Now I'm frowning.
So no one group can do this alone. That's why bringing in things like standard computer animation software wherever possible makes a lot of sense. Working with Kino Corsi and OpenSim project again, the concepts of interfacing with the web and building more collective models of consciousness so that the data is shared among individual machines is very important. But art is also really important. It's not just engineering. So artists represent more than just a black box problem solving. It also represents creativity. Okay, so visual, social, and psychological inventions are what artists, writers bring to the mix. This is an informal kind of invention. There's not science to that. However, we may be able to reverse engineer some of those processes to build effectively a neuroscience of art, but also realize bold new forms of art that are meaningful to us, that we love. It enriches our lives, and adding that value, that direct value, then creates an economy around these kinds of machines. So my background is not just engineering, but also art. I sculpted these fish for the Atlantis Casino in the Bahamas, and I worked on Disney's Tokyo Disney Land and Tokyo Disney Sea. So I have this background in narrative art, writing, an undergraduate degree in film, and I bring all of these things to bear to develop robots that are kind of like portraits that are personalities wherever possible. Collaborating with David Byrne in one of those machines. This Bina robot was a collaboration with the Terrasim movement, a portrait of Bina Rothblatt. And also developing a consumer product that we call Xeno that is both a platform for AI research and a character that hopefully people can fall in love with. So the cognitive, I'm going to just kind of wrap it up here because there's more to show, but we're out of time. So I think we need to cut to questions, right? So. Oh, okay. So part of the research that I'm doing is research into has been research into the uncanny valley, because we don't. This idea of the uncanny valley is that people respond very negatively to realistic robots, but it has never been proven, and we don't know what's happening inside people's minds. So therefore, avoiding realistic robots or neorealism is not the right answer. Testing it is the right answer. So I did some cognitive science studies where we sort of tweaked it, and it really confounds the uncanny valley. It shows that that we don't understand what's going on, but if we use artistic techniques, then we can make near realistic robots very appealing, or make them very strange. So. It's more general theory to consider realism sensitivity and also character coherence. So investigating some of these principles for designing realistic robots then allows us to put these robots into neuroscience tests like this, like some neuroscience research that we've been doing with University of Messina and University of Pisa. Also, classic neuroscience research into human-to-human perception gives us some information about how to engineer these robots, and it results in some, robots that we don't know. We don't know what happens when people perceive these robots that we develop, but it feels interesting and it's pretty compelling when people are interacting. But beyond just developing these robots, we need to unlock what it means to be creative. What are the physics of creativity? And minds are more creative than any other entity in the universe, it seems. And there's some kind of strange loopiness, as Hofstadter says, that seems to be behind that. So the key points are character machines need cognition to be appealing to people. As people demand them and want them, then that provides a market pressure for friendly artificial intelligence. Most robots in the world, a lot of robotics research, are not related to human-like cognition. And if these kinds of machines become human-level intelligent or greater, then they may not really understand us, and we may not understand them, and they would be aliens. And even if they don't pose a threat to us, we may pose a threat to them just out of our fear, because they're not part of our tribe. They're not part. We don't feel like they're part of our family. So character robots will build better relationships with machines. And, yeah. Thank you.